Hi my dear brilliant subscribers, welcome to my channel. This is continuation of Glasstone and Sesonske book, chapter wise. This is second chapter. What we discuss in this video, radioactive equilibrium. In the previous class, I explained about radioactivity, decay constant, half-life, mean life. Now, we discuss clearly about radioactive equilibrium. What are the types of equilibriums are there? How the equilibrium attains? What is the condition to attain equilibrium? That we discuss step by step. Okay. You know, any radioactive nuclide that will undergo decay with definite rate as per the decay constant. For example, if you take thorium-232, if it absorbs the neutron, it will become thorium-233. It will undergo beta decay, it will convert into protactinium. That protactinium also undergo beta decay, it will convert into uranium-233. Here you see the parent nuclide, the initial, the starting which is undergoing decay, that is thorium-233. That is a parent nucleus, parent nuclide. Okay. That parent nuclide undergo decay as per the equation dN by dt is equal to minus lambda n. But the daughter nuclide, that is protactinium, thorium-233 undergone beta decay and protactinium formed. This protactinium also undergo beta decay, it will convert into uranium-233. So here, if you focus protactinium-233, it is produced due to the thorium-233 and protactinium itself undergoing decay. So at the beginning, if you think protactinium-233 is 0, over the period of time, this thorium-233 undergoing decay and converting into protactinium-233. So here what is happening? How the protactinium activity is changing? Is it following like dN by dt is equal to minus lambda n? No. It has two components. This protactinium is produced due to decay of thorium-233. At the same time, it is undergoing decay also. So it has production rate and decay rate. So dN by dt equal to production term minus decay term. Two terms will be there. So in that case, how this particular radioactive nuclide activity changing with the time, you can calculate by using the following differential equation and solving the integral part of the equation. If you continue this equation, if you continue this video, you will understand that. Okay. You see here A, B, C, D, dash dash X you are seeing, no? These are all radioactive elements. The first one is the parent of natural radioactive series. This is the first one. So this is undergoing beta decay with a disintegration constant lambda A, and it will convert into B. And B also undergoing decay, it will convert into C. Similarly, C also undergoing decay, it will convert into D. Finally, one nucleide forming, that is X, that is stable nuclide. So until it reaches one stable nuclide, this radioactive products are continuously undergoing decay. Okay. So the beginning, the first one, what I am calling, this is the parent of natural radioactive series. So B is formed because of A. So that is why A is parent, B is daughter. Similarly, B also undergoing decay, converting into C. So in this case, B is parent, C is daughter, and so on. You understood, no? The first one, the parent of natural radioactive series, it will undergo decay as per the equation n is equal to n0 into e power minus lambda t, no? Okay. So this A is continuously decaying. Here B, what happens? B is produced by the decay of A. So B is producing by decay of A and B is decaying to C. So this B is changing by two ways. One is due to A decay, A is decaying. Another one is itself, B is decaying. So B is producing as well as dying because of decay. In these situations, how we can find out how number of nucleides of type B are varying with time t, we have to calculate. Okay, this is very simple equations. We can solve it. You can very well understand. Rate of change of radioactive nuclide NB. Let it NB is number of radioactive nucleides of type B. One B is radioactive nuclide. So number of radioactive nucleides are NB. How it is changing with time? That is dNB by dt equal to, it is produced due to A. So lambda A Na. Lambda A Na is decay of A. Decay of A is nothing but it is converted into B. And this term, second term is decay of B. B is decaying, no? B is decaying to C. So the rate of change of radioactive nuclide with respect to time equal to lambda A Na minus lambda B Nb. Lambda A is radioactive decay constant for A. Lambda B is radioactive decay constant for B. Okay. Now I can take this lambda B Nb this side. So how can I write dNb by dt plus lambda B Nb equal to lambda A Na. So this differential equation you have to solve to find out how the radioactive nucleides Nb is changing with time. This is simple integration. You can very well solve. See here, both the sides I am multiplying one integrating factor e power lambda b into t here and here. Why I did this? Here lambda b is there, no? So that is why I have used here lambda b. So both the sides we are multiplying, there is no issue. Why I am doing like this? You can do integration very easily by doing like this. If you differentiate nb into e power lambda bt, you will get this one. Now you can very well do integration both the sides easily. So Na is number of radioactive nucleides of type A. that is a parent radioactive nuclide Na is changing exponentially. This you know, Na is equal to Na0 into e power minus lambda A into T. But Nb, how it is changing, we have to calculate. So finally Nb changing with time, that we can solve by substituting this Na, here Na is there, no, equal to Na0 to e power minus lambda A into T. The final equation, how it is coming, I will show you. So after integrating, you are getting this equation, Nb e power minus lambda bt equal to this one, lambda A Na0 by lambda b minus lambda A e power lambda b minus lambda A into T plus C. C is integration constant. We have to find out by using the conditions, initial conditions. At time t equal to 0, Nb equal to Nb0. That you have to substitute. Okay. So you substitute t equal to 0 and you substitute Nb equal to Nb0. You will get the C value. C value is this one, what you are seeing. Okay. After that, you substitute the C value here. Then you will get Nb. Exactly like this. Nb equal to lambda A Na0 divided by lambda b minus lambda A in the bracket e power minus lambda A into T minus e power minus lambda b into T plus Nb0 into e power minus lambda b into T. You see beauty of the equation. If there is no parent nuclide, so this term we can eliminate. Suppose Nb itself is the parent, Nb equal to Nb0 into e power minus lambda bt. This is the general equation for any radioactive nuclide. But this term is coming due to Nb is produced by the parent nuclide and Nb also decaying. So this is the decaying. Okay. Now by seeing these equations, we can understand how the half-lives of parent nuclide and daughter nucleides affects this equation. So what are the equilibriums it can attain after certain time? So what must be the condition so that this Nb and Na attains some kinds of equilibrium? You see this term, at time t increasing for a long time, for infinite time, what happens? This becomes 0, this also becomes 0, this also becomes 0. It means at infinite time, number of radioactive nucleides becomes 0 because it is undergoing decay. Agree? Long time matlab infinite time. At infinite time nothing will be left. So that condition satisfying for this equation. But at certain time t, how they will be in equilibrium? That is Nb and Na0 or Na. Nb and Na. Nb is number of radioactive nucleides of type B at time t. Na is number of radioactive nucleides of type A at any time t. Okay. There are two types of radioactive equilibrium. One is transient equilibrium, another one is secular equilibrium. What is the condition it will attain a transient equilibrium? Suppose there are series of natural decay, the radioactive nucleides, suppose A, B, C, D and so on, X. radionuclides are there. A is converting into B, B is converting into C, C is converting into D, and so on. Finally, it will reach one stable nuclide. Okay. So here, if you focus A and B, B is produced due to the decay of A. So the half-life of parent nucleide is more than half-life of daughter nucleide. Remember this. If half-life of parent nucleide is more than half-life of daughter nucleide, there is a finite probability the series, especially this parent and daughter A and B, attain transient equilibrium. Means Na by Nb or Nb by Na ratio is constant, but the absolute value of Na and Nb are changing. Na means, number of radioactive nuclides of parent, that is A, type A I told no. Nb means number of radioactive nuclides of daughter. Daughter means B, type B. Okay, A is parent, B is daughter. No, this is Na, this is Nb. That's it. So this A half-life is higher than B half-life. In that condition only, there is a finite probability it will attain a transient equilibrium. Okay. Here one condition we will assume. If the parent has an appreciably longer half-life, what is a parent? A. A is parent. Who is daughter? B. B is daughter. Parent has longer half-life. So half-life and disintegration constant, you know the relation. T of is equal to ln 2 divided by lambda. So half-life and disintegration constants both are inversely proportional. So parent nucleide has longer half-life compared to daughter. It means lambda A is less than lambda B. Okay. Then what we can say, at the beginning of this decay series activity, when we are considering, number of daughters will be 0. At the beginning, suddenly, before A is converting into B, so number of B nucleides are 0, no? So we can assume Nb 0 is 0. Okay. So you can substitute Nb 0. This is initial radioactive nucleides of type B can be 0. So this term will be 0. Okay. Then what else left? We have to see these two terms. One is e power minus lambda A into T minus e power minus lambda B into T. Here lambda A is smaller. Lambda A is smaller means this term is dominant because e power minus lambda A into T, it means 1 by e power lambda A into T. So lambda A is smaller means this term is more than this term. So at certain time t, you can neglect this one. This term you can neglect. Because lambda A is smaller than lambda B, this term is very, very small compared to this term. You're understanding now? So this term is small compared to this. So this can be neglected. Then what else left? Only this is left. E power minus lambda a into t. E power minus lambda a into t. Na0, Na0. Lambda a and lambda a as it is. Divided by lambda b minus lambda a. So this one NB equal to lambda a divided by lambda b minus lambda a. Na0 into e power minus lambda a into t. This is nothing but Na. Na is number of radioactive nuclides of type A at any time t. Nb is number of radioactive nuclides of type B at any time t. So this I can replace with Na. Agree? Nb equal to lambda a divided by lambda b minus lambda a into Na. This Na you can take this side, Nb by Na you can write. You will get lambda a divided by lambda b minus lambda a. What is that? A constant. How it looks? It looks like this. Nb divided by Na approximately equal to lambda a divided by lambda b minus lambda a. This is called transient equilibrium. At any time t, the ratio of number of daughter nucleids to number of parent nucleid remains constant, but this Nb is changing with time, Na also changing with time. It means absolute values of Nb and Na both are changing, but their ratio is constant at any time. That is called transient equilibrium. If anybody asks you what is the condition for transient equilibrium, this one, Nb by Na equal to lambda a divided by lambda b minus lambda a. So what is the condition for this actually to attain this equation? The half-life of parent nucleid is appreciably higher compared to daughter. Then only it is possible. I am repeating again. Half-life of parent nucleid is appreciably higher to daughter. Then only this equation or this transient equilibrium is possible. Okay. Another one is secular equilibrium. Secular equilibrium means A, B, C, no? This is A converting into B, B converting to C. So the B is producing and decaying. B is produced by A and B itself is decaying. So at particular time, the production of B equal to decay of B. So suppose 10 type A nucleides are converting into B. At the same time, this B also decayed equal number. So this B, number of nucleides of type B remains constant. You are understanding? Suppose this B is 100 atoms are there. A decayed by 10. So 100 plus 10, 110. But in the same time, this is also decaying, no? 10 decayed. So 10 is coming, 10 is going. So it is always maintaining 100. It's like that. So dNB by dt, rate of change of radionuclide of type B, equal to 0. Because it's not changing. So that is called secular equilibrium. For that, lambda A Na equal to lambda B NB, that you can see. Okay. One more equilibrium also we will discuss. Here also we have to make a condition, that is the parent has a very long half-life. In the previous case, appreciably higher, but here very long half-life, so that lambda A is very small. In the previous case, it is smaller to B. Lambda A is smaller to lambda B. But here, lambda A is very small in comparison with lambda B. It means you can neglect lambda A in the equation, in this equation. Lambda A here, because lambda B minus lambda A approximately equal to lambda B only. Just like 1 lakh rupees minus 1 rupee, approximately 1 rupee only. So this denominator lambda B minus lambda A, I can write is approximately equal to lambda B. It is comparison only. You don't think that lambda A is 0. Lambda A is not 0, but it is very, very small compared to lambda B. Just now I told, no, 1 lakh minus 1 approximately equal to 1 lakh only. So I can write lambda B minus lambda A equal to lambda B only. So you will get like this, lambda A by lambda B. NB by NA is equal to lambda A by lambda B. So what is the condition finally you are getting? NB into lambda B equal to NA into lambda A. Okay. Now you do cross multiplication. You will get lambda A into NA equal to lambda B into NB. This is the condition for secular equilibrium. Secular equilibrium. What is the condition? You have to write this lambda A NA equal to lambda B into NB. So here, what is the specialty of this one? This NB divided by NA equal to a constant value, the ratio also constant. Here what you have to wonder is, just now I told the ratio of NB and NA is constant. Not only that, the absolute amount of B also remains constant. It means number of daughter nucleides remains constant. In that case, it attains secular equilibrium. Parent nucleides are decreasing, but daughter remains constant. How it is possible? Because daughter is produced due to the parent. It should accumulate, no? But it's not accumulating. What happened? B also decaying. So how much produced B equal to that many decayed. So at some time t, after some time t, the production equal to decay. In that condition you are getting this. But very beginning also you can apply this relation for secular equilibrium in the equation I will show you now. In the beginning I have shown this equation dNB by dt equal to lambda A NA minus lambda b nb. This dnb by dt, rate of change of radioactive nuclide with respect to time t, means how nb is changing with respect to time t. In secular equilibrium, nb is constant. Nb is number of daughter nucleides at time t remains constant at time t, it's after some time t. So dnb by dt becomes 0. This is 0. If this is 0, then what you will get? 0 equal to lambda a na minus lambda b nb. You can take this side, you will get lambda a na equal to lambda b nb. For secular equilibrium, simply you substitute this term 0, you will get this relation. You got it now? So this is how to convert units Becquerel to Curie. Simple equation. You know 1 Curie equal to 3.7 into 10 to the power of 10 Becquerel. Becquerel means 1 Becquerel is equal to 1 disintegration per second. So that's what this. So disintegration per second is nothing but Becquerel. So Curie is very biggest unit. So if you have given the activity in terms of becquerels, you can convert into Curie like this. Activity given in becquerel divided by 3.7 into 10 to the power of 10. You will get the answer, the activity in Curie. Okay. In general situation, if you want to calculate activity in terms of Curie or becquerel, if half-life and number of radioactive nucleides are given, so activity, you know, lambda into n is activity. So lambda is equal to what? You can write 0.693 divided by T of 0.693 divided by T of, that is lambda into n, that is in becquerel. Okay. So if you want this answer in Curie, so this is the formula, 1.87 into 10 to the power of minus 11 divided by T of into n, that is in Curie. Here T of must be in seconds. Be careful. The half-life should and must, you should convert into seconds, then you substitute, you will get activity in terms of Curie like this. Here what you required, total number of nucleides n is required and half-life in seconds is required to get the answer in Curie. Here to get the answer, here to becquerel, this is the formula. To get the answer in becquerel, so number of nucleides n is required and half-life in seconds is required. So to get the answer in becquerel, this is the formula. To get the answer in Curie, this is the formula. You understood, no? Gamma rays. How the gamma rays are coming? The gamma rays are coming from the nuclide when nucleus is in the excited state. When nucleus in the excited state means the nucleons, protons and neutrons are in excited state. When they are in the ground state, there is no release of gamma rays or electromagnetic wave. When they are excited to first excited state, second excited state and third excited state. When they are jumping from, suppose particular nuclide is in the excited state of state 1, it is jumping from first excited state to ground state, it will release the gamma ray. Suppose if it is excited to second excited state, from second to ground it can come, or second to first and first to ground also it can come. So which is a high probabilistic? It will come from second to ground or first to ground, or second to first and first to second. Which is highly probabilistic? That You watch forward, you will understand. You know, from the quantum theory, the energy of photon of a gamma ray or any electromagnetic wave. For any electromagnetic wave, energy of the photon equal to h into nu. H is Planck's constant, nu is frequency, nu equal to c by lambda. So I can write hc by lambda. If energy E is given in terms of mega electron volt, we can calculate lambda. H value is given 6.63 into 10 to the power minus 34 joule second. So you can substitute H value and C value. C is the velocity of light in vacuum, that is 3 into 10 to the power 8 meter per second. So lambda you can calculate like this. Lambda is wavelength of electromagnetic wave. It can be anything. But here I am using energy of gamma ray or electromagnetic wave in mega electron volt. So mega electron volt energy is there, means it must be gamma ray. So I can say very well this formula is valid for gamma ray because energy E I am substituting in terms of mega electron volt. Otherwise, if energy is very small, you convert it to mega electron volt and substitute here. In that case, it is valid for any electromagnetic wave. There is no doubt, there is no wrong in that. So I can say this is valid for any electromagnetic wave, but you have to convert E energy into mega electron volt. Then you substitute, you will get the correct answer. So wavelength of electromagnetic wave in meters, the answer will be in meters. The formula is like this: 1.25 into 10 to the power of minus 12 divided by E. E is the energy of electromagnetic wave. E must be in mega electron volt. The nuclear excitation energies are generally in the range of 0.1 MeV to 10 MeV. You see the figure, this is the ground state. This is first excited state. This is second excited state. Inside the nucleus, the nucleons are in excited state, like proton or neutron. They will come to ground state and they will release the energy order of mega electron volt. You see here, if the nucleon is in the excited state here, excited state 2, so it can come directly to the ground state, or if it is in excited state 1, it can come like this also. If it is in the first excited state, it will come to the ground state. This transition occurs with high probability. But the nucleon in the second excited state or even higher, from second excited state to the ground state, this probability is very less. Why? The reason is, based on experimental observation also it is observed, in higher excited states the nucleon jumps from second to first, then first to the ground. If nucleon is here in the excited state 2, it jumps to directly ground state. It emits only one gamma ray of energy equal to E2. So this probability is very less. Instead, it should and must jump from here to here, second excited state to first excited state, it releases one gamma ray. From here to here, you jump again, another gamma ray. So instead of only one gamma ray coming here, this probability is less compared to two gamma rays coming due to jumping from second excited state to first and first to the ground state. The total energy remains constant. Agree? Then how it looks, I will show the another figure. Now you remember in this video the probability of jumping a nucleon from second excited state to the directly ground state is less. Okay, this probability is less. You remember this concept from this figure. See here, this is ground state, first excited state and second excited states. So in the previous figure, it is jumping from here to here, the energy released is E2. So which is very less probability. So now what happens actually? It's supposed to jump from here to here, second excited state to first excited state, and emit a gamma 3. Gamma 3, gamma ray with energy E3. The energy levels of excited states. Okay. From here it should jump again. It will emit one more gamma ray, that is gamma 1. The energy difference is E1. So here the gamma 2 directly from here to here, that is E2. E2 must be equal to E3 plus E1. Energy has to conserve. So here what you have to remember, the nucleon which is in excited state, it will jump from second excitation state to first excitation state and first excitation state to the ground. So this gamma ray emission is highest probability. The probability these transitions are highest compared to this. I can call this as a forbidden states. Forbidden transition, I want to call them. Forbidden transition, because this probability is very, very less. You understood, no? I hope you understood this video completely. In the next video, I will discuss about interaction of alpha particle and beta particles with matter. Okay, till next video, bye bye.